have Damien Stehlé is our chief science officer here at CryptoLab. He was a professor in Lyon and an expert in quantum resistant cryptography and fully homomorphic encryption. His publications have actually appeared in the flagship conference in theoretical computer science, cryptography, and cybersecurity. He also co-authored the Kyber encryption scheme, dilithium signature scheme, and is going to walk you through a few of our standards in FHE. So please welcome Damien Stehlé.
Thanks for the introduction. Thank you everyone for coming here. I hope it will be a very useful event for you. So the purpose of my talk is to go into CKKS performance, because when you go online and look for performance figures for FHE in the literature, it can vary up to several orders of magnitude, depending on where you look at. So I think it's important to give precise figures. Before going into performance, I just want to set the ground because I'm giving the first presentation, so I feel somewhat obliged to recall a few things about fully homomorphic encryption and CKKS. So fully homomorphic encryption, that's a type of encryption scheme with a key generation algorithm, an encryption algorithm, and decryption algorithm as usual encryption. But it has a special algorithm called eval. And this evaluation algorithm takes as input an evaluation key, a bunch of ciphertext, and a function to evaluate, and it returns a ciphertext. And what's the property of this eval? The property of this eval is that if you encrypt messages, you run the homomorphic evaluation on the ciphertext, and then you decrypt. It's exactly the same as if you were evaluating F on the messages in the first place in the clear. So typical scenario would be to outsource computations. So if you want to outsource computation, what's being used today in most cases is a trust-based solution between a client and a server. So say the client wants to externalize computations. Hopefully, the client will encrypt the data to the server and send the function F. And then what will the server do? Because at this stage, the servers don't use FHE. The server would just decrypt the ciphertext, get the messages, evaluate the function, and possibly re-encrypt the function, send it back to the client who decrypts. The big issue here is that the server sees the data. So basically, anyone on the server can look at what is going on. Whereas the FHE-based solution would be different. So the client would still have messages and the function F to evaluate on the messages. It would encrypt with an FHE scheme the messages and send the function F. Then the server would homomorphically evaluate F on the ciphertext. So in particular, the server never decrypts. The server doesn't need the secret key. And this resulting ciphertext C prime is being sent to the client, and the client has the decryption key, so can decrypt. The result of this process is that the server doesn't see the data. So it preserves the confidentiality of the data. So a few key properties of FHE. Computations are as exact encrypted as in plain text. So not like differential privacy, for example, where you lose on the accuracy of data. Interactions are very limited. So basically, the client is sending one message to the server is sending back one message, not like MPC. Ciphertext can be reused, and security holds under well-established harness assumptions, mathematical intractability assumptions, not like what's being called confidential computing, or TEs. Okay, so let's keep going. So CKKS is a bit special as a fully homomorphic encryption scheme because it evaluates functions homomorphically, but on real valued data. So in particular, the plain text space, the native plain text space of CKKS is vectors of complex numbers. So C to the n over 2, where n is a parameter of the scheme called the ring degree. So to think about the ring degree, think of n equal 2 to the 15 or 2 to the 16. So it's very large dimensional vectors. And we can and then we have these real numbers or complex number represented with up to some precision, so maybe 20 bits of accuracy. And what can we do on them? We can add in parallel. We can multiply in parallel, so take two vectors and multiply component-wise. We can conjugate, so do complex conjugation of the vectors in parallel. And so all of this is in parallel, so the coefficients don't interact. And if we want to start making, if we want to have the coefficients interact, then we can rotate the vector. So like shift all the entries by one, for example, and the one that is at the end is put back in front. And this we can do for any an arbitrary amount of shift. Okay. So importantly, CKKS is level-based. So, and multiplication consumes one level, whereas all the others, addition, conjugation, and rotation, they don't consume any level. So they are level free. So at the beginning, because of security, we have a limited number of levels. So given security provides us a limited number of levels for a given ring degree. So we can multiply a few times. And then when we reach the bottom, level 0, then we have to do something. And there is this complex procedure called bootstrapping, which allows to regain levels. And with bootstrapping, then we can keep going forever. So importantly, bootstrapping is much more expensive than the others. And because bootstrapping is so expensive, when we do algorithm design for FHE, we're interested in algorithms that don't consume too much multiplicative depths, because if we consume multiplicative depths, eventually we'll have to pay for bootstrapping or more bootstrapping. Okay, so let's go into bootstrapping. So as I mentioned, it's the most expensive step in CKKS. So here I'm taking some arbitrary parameters, but which are somewhat representative of what we choose in practice very often. So ring degree 2 to the 16. So the vectors have dimensions 2 to the 15, 32,000 entries. Precision 22 bits, and the number of levels which is provided, which is of the order of 13. So remaining levels in the sense that these are levels that can be used for computations and that are outside of bootstrapping, because bootstrapping also consumes levels, but we cannot compute with those levels that are reserved for bootstrapping. So in single thread CPU, real bootstrapping, which just looks at n/2 real numbers, takes 5.3 seconds in single thread CPU. Complex bootstrapping, which takes n real numbers and packs them into n/2 complex numbers. This one takes about 7 seconds in single thread CPU. Okay, but interestingly, we have GPU. We have a GPU code for this. And with GPU, we essentially gain a factor 100. So real bootstrapping gets down to 50 milliseconds, and complex bootstrapping goes down to 60 milliseconds. And that's the order of magnitude for the difference between our CPU code and the GPU code. We typically expect a factor 100. And here you can see it's actually a little bit more than 100. I'm not cheating on the GPU. So this GPU, RTX 4090, is not more expensive than the CPU that I'm using. It's a relatively cheap GPU. Okay, so now once we've bootstrapped, we can do a bunch of ciphertext multiplications. And we can use all the slots to do ciphertext, to do multiplications. So we can use all the 2 to the 15 slots. Also, once we've bootstrapped, we can multiply a few times sequentially. So we can amortize the cost of homomorphic multiplication over both the dimension of the vectors and the sequential multiplications, including, I mean, in the cost, I'm including bootstrapping. So I'm counting a whole bootstrapping loop, which has a bootstrapping and then a bunch of multiplications. And then we can also amortize if we have several ciphertexts that we are playing together. And in this case, the amortized cost of multiplication on the GPU is now of the order of 70 nanoseconds. So it's much, much smaller than different things that we can see in papers. Okay, so to stress, to push the limits of the library and the algorithms, we played a game a few months ago So we try to implement an LLM inference, so a large language model inference. So think of ChatGPT, but a little bit smaller than ChatGPT 3, and a public version of it. So we took Llama 2 7B, which is a fairly large LLM, but not one of the largest. So what is it doing? So it's doing what's called an RMS norm, which is a renormalization of a vector. So we divide the vector so that it has Euclidean norm equal to 1. So this happens in dimension 2 to the 7, but there are 2 to the 12 of them in parallel. So a very large number of them in parallel. Then there is some linear algebra step, which concretely is a plain text ciphertext matrix multiplication. The plain text matrix is 2 to the 12 times 2 to the 12, so 4,000 entries times 4,000. And the ciphertext matrix is 2 to the 12 times 2 to the 7, and we are doing 3 of them in parallel. Then come a step of ciphertext matrix multiplications, where both matrices are encrypted. Dimensions are smaller, so these matrices are 128 times 128, but we are doing 2 to the 5 of these multiplications in parallel. Then comes something different, a softmax. So softmax is kind of a max of many entries, but a smoother version of it. And this softmax, so it's difficult because it's very nonlinear as an operation, and it also looks at many entries. So the entries are not acted upon in parallel. The entries, we need to look at all the entries and mix them together. So softmax is in dimension 128, 2 to the 12 of them in parallel. Then more linear algebra, an RMS norm, more linear algebra. So this one is the largest one. So the matrix dimension is now, the plain text matrix is 2 to the 13.4 times 2 to the 12. A SILU, so SILU is something different again. So it's an activation function. It's a bit simpler than softmax because it acts in parallel on the entries, but it's also very nonlinear. So it requires multiplicative depth. 2 to the 20 of them in parallel. More linear algebra. Once you are done with all this, you repeat 32 times. I've got no idea why. These LLM guys, I don't understand what they're doing. We just took their algorithm and look at what we can do homomorphically. Maybe. So this gives you one output token. So if you want more output tokens, you repeat more of the same. So the next tokens are a bit simpler, but it's the type of operations are similar. Okay, so if you count, to get one token, it's about 2 to the 42 bit operations. So that's what we are evaluating homomorphically. And for the sake of comparison, I'm looking at AES. So AES is of the order of 2 to the 14 bit operations. And I'm taking this example because AES, homomorphically evaluating AES, has a long history in the homomorphic encryption community. It was used as a test case to see how efficient is homomorphic encryption and how much progress we make. So the task that we are considering here is almost 2 to the 30 times more expensive than an AES encryption. And this we get with 8 GPUs in about 3 minutes. So it's not real time, but it's feasible. If you're okay to wait a bit for the answer, then it becomes reasonable. Okay, so now I want to go into binary circuits. So very often, when you read papers, people will say, if you want to play with real numbers, use CKKS. If you want to play with binary gates, use TFHE or FHE. But in fact, CKKS can also be used for binary gates. And this was put forward by Drucker and his co-authors in a paper at the Journal of Crypto this year. So they had a very nice idea on how to use CKKS to do binary gates. And later in this same year, so this team of Drucker and his co-authors, they took CKKS as a black box. And then what we did is that, okay, so if you want to do this, we are going to modify bootstrapping and we are going to modify a little bit the design of CKKS to gain efficiency. So that's what we played with this year with 2 papers. And so if we want to compare, so for example, throughput with single-thread CPU. So I'm taking single-thread CPU to compare apples to apples. But you can remember that if you use GPU, you get a factor 100. So I'll let you do the division by 100 yourself. But so now going back to CPU. So a reference implementation of TFHE or CGGI would cost 10 milliseconds per gate, single-thread CPU. If you use the paper of Drucker and his co-authors, it's of the order of 100 microseconds per gate. So 2 orders of magnitude smaller. And then we pushed it down. And at the paper that we are going to present at Asia Crypt, we are below 10 microseconds. So we are more than 3 orders of magnitude faster in terms of throughput. This is still single-thread CPU. So if you move to GPU, divide by 100. We actually have IDs in the pipe that still lower the 7.4 microseconds per gate. So my goal, my personal goal is to go to 1 microsecond per gate. Okay, so all of this relies on recent research results. So we've been working on the security aspects of CKKS, especially on the in-CKD security, and also on threshold FHE. We've been working, so these advanced security properties or protocols based on FHE, they typically require higher precision. So we also worked on how to get higher precision with CKKS, both for bootstrapping and multiplication. We played with conversions between LW type ciphertext and ring LW type ciphertext, which is very useful to convert from TFHE ciphertext into CKKS ciphertext, for example. We've played with exact computations, as I mentioned in the previous slide, and also on private AI algorithms, or algorithms motivated by private AI, like homomorphic softmax, that we are going to present this week. I don't remember if it's today or on Thursday at CCS. And an algorithm on plain text ciphertext multiplication. Okay, so what's coming next? So we are still, there are a bunch of research results in the pipe that should provide further accelerations. So there is a step of integrating what's being published. So when we get the research results, we have experimental code to test in practice what they mean. And we write, we publish, and then this experimental code has to be translated into production level code, and that takes time. So we are in the process of this for some of the techniques. So the default library will be accelerated just because we integrate progressively the recent research results. So that's about the underlying arithmetic will go faster. CKKS on exact data will become significantly faster also in the next few months. And we didn't integrate, so for the LLM figures that I gave, we use the homomorphic softmax that I mentioned, the papers that we are going to present this week, but we didn't use yet our accelerated plaintext ciphertext matrix multiplication. So that will also give an improvement over the LLM figures. And very soon, so we are working on faster threshold FHE, improved bootstrapping. So there are a bunch of ideas floating around to accelerate bootstrapping and hardware acceleration. Yeah, that's it for my presentation.